Alright then, MOSFETs. How do they work? Okay, so this is the circuit that I'll be demonstrating right now. We have in the center there, we've got an IRF 830 MOSFET, 830A actually, gate, drain, source. This is the MOSFET symbol over here. We're using a 9-volt battery, negative rail, positive rail, gate, drain, source. Source is connected directly to the negative rail, as will be the function generator minus black lead and the scope ground. Drain of the MOSFET goes to an LED and a dropping resistor for the LED and to the positive rail. And also we'll be monitoring the drain signal on the MOSFET with the scope probe with respect to ground. Okay. And the gate of the MOSFET is connected just directly to the function generator's plus lead, and we'll be using a square wave of 10 volts peak to peak symmetrically around 0. So it's going plus 5, minus 5, 0. Alright, so actually it's this little leg, I shouldn't have drawn that, okay, because that's not there. It's going to go up, down, up, down, like that. And I'll be varying the frequency of that during the demonstration, okay, because I want to show, the purpose of this demonstration is actually to show the relationship between the voltage on the drain pin and the state of the LED. Because when the drain pin is high, the LED will be off. When the drain pin is low, the LED will be on. How can that be? Well, it's a common misconception, or at least it's common among a certain group of researchers, and that's the cause of a lot of misconceptions and errors in that particular group of researchers' work. So I hope to be able to clear up that that little item today, because when the drain signal is high, the MOSFET will be off. Okay? And that's going to be the case of any N-channel MOSFET that's hooked up in an arrangement like this with respect to the voltages and the gate drives. Alright, so let me show you the actual circuit. There it is right there. Alright, you can verify for yourself. We got the 9-volt battery going into the positive and negative rails. There's the function generator minus and the scope minus. There's the dropping resistor for the LED. There's the wire going over to the drain from the back side of the MOSFET. There's the wire going from the source to the minus rail. Here's the wire coming off of the drain to the scope probe. And here's the wire coming off the gate to the function generator red lead. Alright, that's just the wire from that. Okay, so we're all hooked up. And, okay, now here's the scoposcopy part. Let's see. So, A channel will be the signal from the function generator, and I've got it turned off right now. 5 volts per division, okay, and there's where the 0 line is. B channel will be the drain signal, and let's see. Get that right there. It's also turned off, but it'll be DC coupled at, it says 0.2 here, but remember we have a 10x attenuating probe, so that's actually going to be 2 volts per division. Alright, so let's turn the traces on. There's a little signal from the function generator, and boom, look, as soon as I turn that trace, that trace on, it pops up there. So what are we seeing here? 2 volts per division, 2, 4, 6, something below 7 volts. Alright, and look, the LED is off, right? Okay, so the drain signal right now is high and the LED is off. Alright, so now what I'm going to do is increase the amplitude of the function generator's pulse here. Oh, by the way, we're triggering off of the external trigger. The function generator, as I showed in the last video, is triggering directly, so we have correct phase relationship here between these signals. All right, and right now we're poking along at 2 kilohertz. Okay, so now I'm going to turn up the amplitude, and you'll see that spike there is lead inductance, and then boom, there now the MOSFET is fully on. All right, and here I'll show you what I mean. As we turn up that guy, boom, there's the MOSFET. Can you see that? MOSFET is now fully on. All right, off, on. All right, so look what has happened here. Remember where it is when the gate drive is low, right? It's right up here at a voltage that's somewhat less than the battery voltage, right? Now when I turn the gate drive on, boom, and the MOSFET comes on, the signal is, part of the signal stays up there, and part of the signal goes down here to the baseline voltage, to 0 volts, right? Okay, and the LED is on. And this signal is telling us that the LED is actually flashing at 2 kilohertz, far faster than we can see. All right, so let's slow it down. Let's slow that sucker down so we can actually see it flashing. All right. All right, so here we've gone to 0.4 and 10, so we're at 4 hertz now. 0.4 and 10. 1, 2, 3, 4. I don't know, or 4 flashes per second or something. I don't know, it's flashing kind of slow. Okay, so if you look at the traces on the oscilloscope, the top trace is the function generator, and it's going from -5, +5, -5, +5, -5, +5, -5, +5. The bottom trace is the drain trace, and it's going from low, high, low, high, low, high, low, high. And do you see what the LEDs are doing? On, off, on, off, on, off, on, off, okay? So when the drain voltage is high, the highest voltage of the drain, near the battery voltage, the load will be off. When the drain voltage goes low, 0 volts, ground voltage, the drain, or the load, will be on. Okay, got that? Now earlier, somewhat earlier, I was actually able to get this little circuit to produce the standard Ainsley oscillations, and that's also very interesting. Let me see if I can get it to do that this time. We'll tweak it here a little bit and change the function generators drive settings and just mess around with it a little bit. Maybe give it a little bit more voltage on the gate. Well, I can't seem to get it to oscillate this time. Anyhow, I was at one point able to get these massive oscillations out of it. That's not it there. Well, it doesn't want to do it. No. Oh, that's too bad. Because when the MOSFET, I found out here, that when the MOSFET is, oh, there they were. Oh, they were there for a minute. Oh, come on, baby, you can do it. I found that when the oscillations are there in full force, the MOSFET is almost totally conducting. Or this one is anyway. But it's not going to do it for me now. Of course not. All right. Anyhow. Let's see here. Rosemary says it's fun to tune for these oscillations. I don't know. I've had fun. It didn't resemble tuning for oscillations. See, my construction is so neat that it's hard for me to get these oscillations, but I did get them at one point. Still trying. Oh well. Anyhow, the point of the demonstration is that when the Oh, oscillations! Yeah, baby! There they are! They came. Okay, now they're the MOSFET, the LED's off, but you can see these massive oscillations. Let me change the frequency a little bit. Oh, there they went away for a bit. And now I'm going down on the frequency here. You can see that massive oscillations. There they went away, now they're back. When they're back, the LED's on brightly now, and then if I change the frequency a little bit, slower and slower, sometimes they'll go away. There, they went away. And now we have that standard flashing behavior. And then now if I go back up on the frequency a little bit, just kind of randomly, come on. See, now they don't want to come in. But you saw them. Oscillations. Oscillations. There they are. Look. Woo! All right. Oscillations. There. Now I'm turning up the gain, the amplitude a little bit. Oscillation. And look. Sucker's on. So you think I'm recharging that 9-volt battery now? With the oscillation? Just out of curiosity, let's see if we can figure out what the frequency is of those. Okay, so now we've got 0.2 of a microsecond per division, and let's see, in 1, 2, 3, 4, 5, 6, 7, 8, 9 divisions, we get 1, 2, 3, 4, 5, 6, 7, 8, and plus, say, let's call it 9. 9 divisions are, so that's about us just, oh, wait a minute, we're 0.2 of a microsecond, so 0.2 of a microsecond per period of the waveform, right? That's about 1 division. Let's see here, move it a little bit horizontally. Yeah, so that's exactly 1 division. Just slightly under 1 division horizontally at 0.2 microseconds per division. So do the math and to determine what the frequency is of these massive oscillations. And the function generator setting right now is actually at 3.7 times 10, so it's at 37 hertz. So that sure ain't no 37 hertz. Yeah, okay. Thanks for watching.